Thank you very much for listening to this presentation and for having an interest in our new paper of a novel hybrid automaton framework for multi-phase epidemic modeling, done in collaboration with my colleague Nurdan from the School of Mathematics and Computer Science from the University of Wolverhampton in the United Kingdom. I have a question for you. After 2020 and 2021, what else is there to say about epidemic modeling? Well, probably we have to say that we need better models to reproduce the complex dynamical behaviors involved in the spreading of infectious diseases over different evolution phases. And we need to consider, and it's very important for this, the dynamical discontinuous transitions about all the different phases of the transmission of these diseases, and also considering switching dynamical behaviors. In this paper, we offer a solution for this problem. And in this presentation, I will show you how we have built this new modeling framework. So the first step is to understand that we have a metapopulation model for each phase of the disease. We will propose a modified version of the classical SEER epidemic models, but with more elements. The second step, and this is the completely new thing that we propose, is to consider a multi-phase epidemic model, the different phases of evolution of time of the transmission of the disease with different switching dynamical behaviors. We will use the elegant framework of hybrid dynamical systems, hybrid automata, for the different, to study the different phases of the infectious disease. What is key to realize that in this modeling framework, we will consider switching transmission rate, switching basic reproduction rate ratio, and a switching vaccination strategy. Finally, I will show you the simulation of key scenarios for the dynamical evolution of the probabilities to belong to the different populations that we consider in our epidemic model. And finally, the dynamical evolution of the hybrid automaton for the complete study of all the phases of the disease. Okay, let's go for the first stage of our modeling process. That is having the model for each phase of the disease. So first of all, we need to consider the basic populations in our model. So we consider these populations, and you can see in the figure. So we have susceptible individuals for the disease, exposed individuals, and then this is also an important thing of our model. We distinguish between infected individuals who are symptomatic and infected asymptomatic individuals. We also consider recovered people, and the recovered population is by immunity or by vaccination. So we also consider in our model vaccination strategies. Basically, we consider the proportion of susceptible individuals that have been vaccinated. And also, finally, we consider the dead population. We are not going to consider natural deaths from all the populations. We also consider the deaths from the infectious people, symptomatic and asymptomatic. And we consider an additional ratio of deaths for the infected symptomatic. So here are the relations, and the details are in the paper. Okay, so now having all these subpopulations in mind, we are going to produce the dynamical model for the evolution of the different populations. But in this case, we are going to in this case, we are modeling not the subpopulations, but the time-dependent probabilities to belong to these subpopulations. But what I would like to highlight in this model for each phase I of the disease is that these are the key features that we are introducing, putting together all these things that make our model quite complete in comparison to other models that they had been proposed before. So first feature is that we distinguish between asymptomatic and symptomatic infectious people. Also, we consider an immunity period inside the model. And what is key also, so we have the switching beta, which is the transmission rate. So we have a switching transmission rate and a switching vaccination strategy. And of course, as a consequence, we have a switching basic reproduction ratio of the disease, R. This famous R that we have been listening to it during all these 2 years. Okay, so this is the model, and I have put in red the introduction of these key features. So more details are in the paper. So now with this model for each phase of the disease, we go to the multi-phase epidemic model through our hybrid automaton framework. So we have multiple phases of the disease, M phases with switching, transmission rate, vaccination strategy, and basic reproduction ratio. So the phases of the disease that we are considering is free movement. So the epidemic is under control or non-existent. Uncontrolled spreading. So the spreading of the disease increases, but no measures are in place. Confinement, when the situation goes worse and we have to have hard restrictions to stop the transmission of the disease. And we have a set, finally, of P deconfinement phases that they are between confinement and free movement. The result of all of this is this hybrid automaton, and in each discrete location of the hybrid automaton, we put our model that I was explaining before for each phase of the disease. And each of these, they are going to have a different transmission rate, basic reproduction ratio, and vaccination strategy. And we have here, which is important, all the transitions, dynamical transitions between all the different phases of discrete locations, depending on the dynamics of all the probabilities of belonging to the subpopulations. For example, if we go to the free movement case, so phase, so we stay there if the number of infectious people do not increase, so it is constant. We go out to uncontrolled spreading if this number is increasing, but we can go to confinement if the number of exposed individuals are greater than the susceptible individuals. All the details for all the transitions are in the paper, and I cannot stop to explain all of them. So let's go for the simulation of results. So let's see the dynamics of the probabilities to belong to the different subpopulations. Here I have put 4 scenarios. So we simulate the model, the SAYART metapopulation model. And for example, for the first scenario, if we have a low transmission rate, a high proportion of infections of I versus A, and a good proportion of people vaccinated at a high immunity period, this is ideal. So the susceptible go down very quickly and the recover are high. But look, for example, here, if we have more people vaccinated, but we have a high transmission rate. So the exposed increased considerably in comparison to the scenario number 1. And look here, for example, in a scenario 3, when we don't have vaccinated people, the exposed are very high and the recover are less. If we have all the people vaccinated, look, this is ideal. So the recover are very high, then susceptible go down very quickly. This is the simulation of our hybrid automaton. So for each phase, we are going to have a different strategies that I was explaining before. Look, for a non-suitable vaccination strategy, we are seeing that it seems that it was a correct strategy, but at the end, after free movement, we go to confinement. But if we have a suitable vaccination strategy after the confinement, so then we go to free movement forever. Okay. This is more a qualitative analysis than quantitative. So as a conclusion, I can say that hybrid dynamical models of infectious diseases are very good for the producing the dynamical evolution over time of the phases of an infectious disease. Also, it's good for designing new scenarios and producing better contention, deconfinement, and vaccination strategies. They are good for better understanding how complex dynamical interactions are produced between subpopulations. And finally, these models are good for discovering what we do not know yet, not just to reproduce what we know already. So I'm open to questions. Thank you very much for listening.